Welcome back to our channel. Today, we're diving into Module 6 of the CompTIA Security Plus Guide to Network Security Fundamentals, 8th edition. This module is all about mobile and embedded device security. By the end of this video, you'll have a solid understanding of mobile devices, how to secure them, and the unique security considerations for embedded and specialized devices. If you find this content helpful, please like, share, and subscribe to help keep our channel going. Let's get started. So, what will we cover today? By the end of this module, you should be able to list and compare different types of mobile devices and their risks. Explain how to secure a mobile device. Describe the vulnerabilities and security considerations of embedded and specialized devices. Explain how application security can provide protections. Let's begin with mobile devices. There are several types, each with unique features and risks. First, we have tablets, which are portable computing devices that typically don't have a built-in keyboard or mouse. Next are smartphones, which combine the tools of a feature phone with an operating system that allows you to run apps and access the internet. Wearables, like smartwatches, are devices you wear instead of carry. They offer convenient features right on your wrist. Continuing on, we have portable computers. These devices mirror the functionality of desktop computers but are smaller and can run on battery power. Lastly, web-based computers contain a limited OS and a web browser with an integrated media player. Each of these devices has specific connectivity methods and security considerations. Mobile devices connect to networks in various ways. Cellular networks divide coverage areas into cells, each managed by a transmitter connected to a mobile telecommunication switching office, or MTSO. Wi-Fi, on the other hand, replaces or supplements wired LANs, providing wireless local area network connectivity. Other connectivity methods include Bluetooth, which uses short-range radio frequency transmissions for quick device pairings, and USB connections, which facilitate data transfer between devices using various types of USB connectors. Let's talk about enterprise deployment models. BYOD, bring your own device, COPE, corporate-owned, personally enabled, and CYOD, choose your own device, offer flexibility and cost savings for businesses. They simplify IT infrastructure and enhance employee performance by giving users the choice of device and carrier. However, with these benefits come risks. Mobile devices are attractive targets for threat actors due to their access to sensitive data. Risks include mobile device vulnerabilities, connection vulnerabilities, and the danger of accessing untrusted content. Mobile devices face several vulnerabilities. Physical security is a major concern since these devices are often lost or stolen. Limited updates can leave devices exposed to threats. Location tracking and unauthorized recording are also significant risks, as they can lead to targeted physical attacks or spying. As we discussed, different mobile device models like BYOD, COPE, CYOD, and VDI each come with their own set of benefits and challenges. However, regardless of the model, mobile devices are vulnerable to various security threats when connecting to networks or other devices. One common vulnerability is tethering, where an unsecured device sharing its internet connection can infect others. USB on the go, OTG, allows devices to connect to external media or act as a peripheral, posing risks if a malicious device is connected. Malicious USB cables can introduce malware by acting as human interface devices. Public hotspots are also risky as attackers can intercept sensitive data. Understanding these vulnerabilities is crucial for implementing effective security measures. In the next slide, we'll explore practical strategies to mitigate these risks and protect our mobile devices. Having examined the vulnerabilities associated with connecting mobile devices to networks, it's essential to consider another significant threat: accessing untrusted content. Users might bypass their smartphone's built-in installation limitations, known as jailbreaking on Apple iOS or rooting on Android devices, to download apps from unofficial third-party app stores, a process called sideloading. This can expose devices to unverified and potentially harmful applications. Additionally, untrusted content can infiltrate mobile devices through SMS, MMS, and RCS text messaging. Even seemingly innocuous actions like scanning QR codes can pose risks. For instance, an attacker could create an advertisement for a reputable website but include a QR code leading to a malicious URL. To protect mobile devices, start with strong authentication methods like passcodes, PINs, or biometric authentication. Segmentation can separate business data from personal data, ensuring data privacy and legal compliance. Enabling loss or theft services can help locate a lost or stolen device. If recovery isn't possible, performing a remote wipe can protect sensitive information. Mobile Device Management (MDM) tools allow remote management of devices, while Mobile Application Management (MAM) focuses on app distribution and control. Mobile Content Management (MCM) and Unified Endpoint Management (UEM) provide comprehensive management and security for mobile devices, applications, and content. Knowledge check. Ozan has received a phone call from his supervisor that a new employee has attempted to download and install an unapproved app that allows her to circumvent the built-in limitations on her Android smartphone. What is this called? A. Rooting. B. Sideloading. C. Jailbreaking. D. Ducking. The correct answer is A. Users who circumvent the installed built-in limitations on their smartphone are jailbreaking on Apple iOS devices and rooting on Android devices. Now, let's shift to embedded systems and specialized devices. These include hardware and software integrated into larger systems for specific functions. Common examples are Raspberry Pi, Arduino, and System on a Chip (SoC). These devices often use a real-time operating system, RTOS. Now, let's talk about some cool hardware components. Have you heard of the Raspberry Pi? It's a small, affordable computer that fits in your hand, about the size of a credit card. You can use it for all sorts of projects, from learning to code to building your own gadgets. Next, we have the Arduino. It's similar to the Raspberry Pi but focuses more on controlling physical components like lights and motors. It's great for creating interactive projects. Then there's something called an FPGA, which stands for Field Programmable Gate Array. Think of it like a customizable chip that you can program to perform various tasks. Finally, we have a System on a Chip, or SoC. This is a super smart chip that combines all the essential parts of a computer into one tiny package. Many SoCs use a real-time operating system, or RTOS, to manage their tasks efficiently. Moving on to industrial systems, which are crucial for manufacturing and other industries. Industrial control systems, or ICSs, gather and analyze data to control machines like valves, pumps, and motors automatically. These systems are managed by something called SCADA, which stands for Supervisory Control and Data Acquisition. SCADA helps monitor the systems, keep things running smoothly, and fix issues before they cause problems. Next, let's explore specialized systems. Digital smart meters, for example, measure how much water, gas, or electricity you use. Unlike old-fashioned meters, they offer more precise data and are easier to read. Other specialized systems include medical devices, aircraft, and vehicles. Cars nowadays are equipped with advanced embedded systems that use sonar, radar, and lasers to control things like brakes, steering, and acceleration. Now, let's talk about the Internet of Things, or IoT. This concept connects everyday devices to the Internet, allowing them to send and receive data. Imagine your thermostat adjusting the temperature automatically or your coffee maker brewing your morning cup without you lifting a finger. IoT includes all sorts of gadgets, wearable tech, smart home devices like thermostats and washing machines, even things like electric toothbrushes and light bulbs. In 2022, the average household had about 22 connected devices. That's a lot of smart tech. Security for these devices is critical. SCADA systems, ICSs, and IoT devices have low resilience to attacks. Improving security starts with understanding their constraints and applying hardening techniques. Recent legislation, like the Internet of Things Cybersecurity Improvement Act of 2020, mandates increased cybersecurity for these devices. Knowledge check. Which type of OS is typically found on an embedded system? A. SOC. B. RTOS. OTGD COPE. The answer is RTOS. SOCs often use a real-time operating system, RTOS, that is a specifically designed OS for a society in an embedded or specialized system. Now let's look at some common attacks on systems and how we can defend against them. First, we have the executable files attack. This attack tricks an application into creating or modifying executable files on the system, which could lead to unauthorized access or damage. To defend against this, make sure applications can't create or change executable files unless absolutely necessary. Next is system tampering. This involves using a vulnerable application to alter sensitive parts of the operating system, like registry keys or system startup files. The best defense is to prevent applications from making changes to these critical areas of the OS. Finally, there's process spawning control. Here, attackers trick an application into spawning new executable files. To protect against this, it's important to restrict the application's ability to start new processes. By understanding these attacks and implementing these defenses, we can better protect our systems from potential threats. Now, let's explore the fundamental concepts of application development. When developing an application, we typically go through several stages: development, testing, staging, and production. This process is often described using an application development lifecycle model. One popular model is the waterfall model, which follows a sequential design process. This means each stage must be completed before moving on to the next. On the other hand, the agile model takes an incremental approach, allowing developers to discover and fix software issues as they go, making the process more flexible and adaptive. SecDevOps integrates secure development practices into the application development process using the Agile model. SecDevOps emphasizes automating processes to develop code quickly and securely. It includes continuous monitoring to detect issues in real time, continuous validation to ensure code quality, continuous integration to merge code changes frequently, continuous delivery to make sure the software is always in a deployable state, and continuous deployment to automatically release new features and updates. This approach ensures that security is a key component throughout the development lifecycle. Secure coding techniques are essential to protect applications from attacks. These include proper encryption implementation and memory management to avoid vulnerabilities. Code testing helps identify and fix potential security issues before deployment. Testing is one of the most important steps in ensuring secure and reliable software. It should be carried out during both the implementation and verification phases of the development process. There are two main types of code analysis: static and dynamic. Static code analysis involves testing the source code before it's even compiled. This can include automated tests as well as manual peer reviews. It helps catch issues early in the development process. Dynamic code analysis, on the other hand, is performed after the code is compiled. This type of testing, also known as runtime verification, checks how the software behaves during execution. One technique used in dynamic analysis is fuzzing, which involves providing random inputs to the program to see if it triggers any exceptions. These exceptions might include memory corruption, program crashes, or security breaches. By incorporating both static and dynamic code analysis, we can thoroughly test our applications and ensure they are secure and reliable. Knowledge check. What is another name for runtime verification? A. Static code analysis. B. Dynamic code analysis. C. Fuzzering. D. Weighted code analysis. Answer: dynamic code analysis. Security testing performed after the source code is compiled is a process called dynamic code analysis or runtime verification when all components are integrated and running. What is another name for runtime verification? Self-assessment. Rate your competence of the following module objectives on a scale of 1 to 5, where 5 indicates you have full confidence in your competence of that objective, and 1 indicates you have very little confidence in your competence of that objective. If you self-score less than 4, you should consider reviewing the module and related exercises. 1. List and compare the different types of mobile devices and their risks. 2. Explain the ways to secure a mobile device. 3. Describe the vulnerabilities and security considerations of embedded and specialized devices. 4. Explain how application security can provide protections. That's it for Module 6 on mobile and embedded device security. We hope you found this video helpful. If you did, please give it a thumbs up, share it with your friends, and don't forget to subscribe to our channel for more educational content. Thanks for watching, and see you next time.